potential energy today. So potential energy is the work a force could do. So for instance, if I have this ball here and I release it, gravity can do work and give that ball kinetic energy. Now this often requires a zero reference. Well, how far can gravity pull this ball down? So it can only pull it down in this case till it hits the table, or in a different location, maybe till it hits the floor. So we need that reference height of zero. Or in the case of an elastic spring, that spring is at its equilibrium, there's no force being applied. If I stretch it, well, now that spring can apply a force and bring it back to that equilibrium. So that equilibrium is our zero reference point there. Now, work is telling me about how kinetic energy is changing. So a positive work is increasing the kinetic energy and a negative work is decreasing the kinetic energy. Potential energy is on the opposite end of that equation, meaning if we do positive work, kinetic energy is increasing, but potential energy is decreasing. So our change in potential energy is the opposite of what our work done is. So what we're going to do is we're going to talk about how do we find potential energy at a point, and then how can we use this to create a grand equation, the work kinetic energy theorem. So a point here has potential energy. And when it gets to the ground, it doesn't have potential energy, because when I put a ball on the ground, gravity can't do any more work. So I want to describe how much potential energy it has up at this point. So gravity pointing down will have a negative force of mg, and it can start at h and end at 0, so its displacement will be negative h. And so 0 minus h gives me that displacement of negative h. And so the two negatives cancel out, and I can talk about the potential energy at any point as mgh. Now this does have the acceleration of gravity g, 9.8. That means we do need to be on Earth, and we need to be relatively close to the surface of the Earth. Within 6 kilometers or something gives you a 0.1% change in that g value. So as long as we're relatively close to the surface of the Earth, this works. And then just to kind of note to ourselves that the work done by gravity is going to be opposite the change in gravitational potential energy. Now when we move over to the elastic scenario, for our elastic scenario, that equilibrium point is our 0 point. And so we are always going to have to reference that 0 point. Whoops, I flipped that around again. That's okay. So we can switch that right now. So we're going to start at x and we're going to go to 0. Okay. And in doing so, we're calling this our negative direction, so that's actually a negative force there. Okay, sorry about that. And so when we do that, our negatives will cancel again. We'll be left with 1/2 kx squared. We do have to do the integral because this is not a constant force. Again, the same thing applies. If we have potential energy and kinetic energy, the work is telling me about the direction of motion of energy to or from kinetic energy, so we just have to flip that sign, and we see the change in elastic potential energy is equal to the negative of the work done by the elastic force. So there is our potential energy start. We will talk about potential energy functions for things other than gravity and elastic, but we'll save that for another video.